And our final speaker in the session will be Dr. Jim Head. Before I introduce him, just a reminder that after Jim's presentation, we'll have a 10-minute Q&A period. So please feel free to drop questions in the chat, as you guys have been doing so well throughout this whole session. Thanks for contributing. So our final speaker in the session is an invited talk by Dr. Jim Head, who participated extensively in the Apollo program through a whole host of activities, including but not limited to landing site selection characterization, real-time science support, and astronaut training. So Dr. Head will be providing us with some lessons learned from his experience during Apollo. Take it away, Jim.
Thanks a lot. Sound check, okay?
Yep, loud and clear.
Okay, great. So thanks so much. I think the first thing I would say here is if you want to figure out how to do all this, go back and read Jack Schmidt's abstract and listen to his presentation again. So everything he said is, absolutely on target. And I think all I want to do is try to complement that with a more view from sort of in the trenches and kind of a side view of the process, et cetera. And maybe I can contribute to some of this as well. So next slide, please. So basically, here we are, 50 years after Apollo, and I'm reminded of a comment by essentially Mark Twain, which is something like, history doesn't repeat itself, but it rhymes. So we're not going to try to tell you what to do, but there's a lot of lessons here that are really important. And one of them is exemplified by this 50th anniversary, Next Giant Leap, which is Artemis is on to, go ahead, you can go to the next one. Artemis is on to Mars, and that's a critically important thing here because basically, we need to practice for Mars. That's what one of the major things that Artemis is going to do. Mars is not the moon, not only in terms of its geology, but also in terms of the time delay, in terms of communications with the Earth. So I'm going to first talk briefly about broad setting and sequence of the Apollo missions and some general lessons learned, do a couple of quick examples, Apollo 15 and 16, and then come back for lessons learned. And finally, I have put together a whole series of slides at the end here which address the specific breakout session questions, so I hope those will be useful in the breakout sessions themselves. We're not going to cover those, but they're in this presentation. Next, please. So what did I do? I worked at NASA headquarters as a systems engineer in 1968 to 1973. A critical point for you all is, yes, get young people involved. This was my postdoc. I immediately went from looking at carbonate basin evolution and the Devonian of the Appalachians to working on the Apollo program. So we do need young people. It works, okay? Exploration strategy, we try to figure out, this is a list of my jobs, basically. I was involved with a lot of people in doing these things, what questions to address, landing site selection, where do we go? Traverse planning, what do we do when we get there? Science and engineering synergism, how do we implement the science goals and objectives? I'm going to come back to this one, because working shoulder to shoulder with the engineers is a critically important thing to get going from the start. You need to work shoulder to shoulder every day with the engineers, operations people, the astronauts, etc. Astronaut training, how do we train test pilots? And then, of course, work towards having geologists as crew members, as Jack so beautifully showed in his summary of the Apollo 17 lessons. And of course, we need to do mission simulations. This is really important. You have to practice again and again and again, again and again and again. This is really critical. Mission operations, I worked in the actual missions and building 30 mission control in the science support room. And then, of course, when the astronauts got back, we had extensive post-mission debriefings and analysis. We got their feedback individually and collectively, and then we replanned the subsequent missions. This was the feed forward, et cetera. So these are the things that I base this on. And again, my view here is a bit more of a in the trenches kind of thing, a side view from Jack's excellent summary at the beginning. Next, please. So it's really important to follow up on Renee's point here that Apollo was totally guided by scientific goals and objectives, broadly to understand the nature, internal structure, and history of the moon and its environment. And there were 4 ways to do this. The surface science stations, primarily the ALSEP, the surface exploration, that was the field geology and experiment and some geophysical instruments that were carried, particularly on Apollo 17, the gravimeter, et cetera. And indeed, orbital exploration, the astronaut in orbit was doing science all the way along. And then finally, the moon as a platform. Jack alluded to far-side astronomy implementation. And again, we did that on the moon too, and I'll come to that briefly in a minute. So contrary to a lot of belief of the general community, there was a huge range of science at all levels during Apollo. Next, please. So let's just talk about the Apollo missions. And there's an important lesson here, okay? The first 4 missions, 7, 8, 9, and 10, were precursor missions. You don't just get up, build a spacecraft, go to the moon. You have to test it. Command module 7, getting out of the Earth's gravity field 8, 9 and 10, practicing, in fact, the whole full-up situation, both on the Earth and Mars. This was all prior to, of course, Apollo 11. Next slide, please. Now, the next missions, Apollo 11, 12, 13, and 14, they were also precursors in a lot of ways and very evolutionary. That's the key here is evolution, evolutionary missions, okay? You're not just repeating them, you're learning from each one, and they're all critically important. Next, please. What did those 4 learn? Okay, the first 4 learned, how to land safely, deploy experiments, collect rocks and soils. Apollo 12, increase stay time on the lunar surface, increase the number of EVA periods, and demonstrate pinpoint landing. This was critical. This was critical on Apollo 12 to land next to the Surveyor spacecraft. And then, of course, on Apollo 14, provide equipment for transport of tools and samples with the other, essentially, with a mobile equipment transporter. Next, please. Now, this set the stage for what I would call on 15, 16, and 17, the scientific expeditions of the moon. These were Lewis and Clark-like expeditions with multiple objectives, incredibly involved in, 3 EVAs, a lunar rover, a whole variety of things that enable really Apollo 15 to be the first scientific expedition, 16 and 17 to follow on and perform beautifully, even better each one. Next, please. So I want to turn now to see what this required. This is what science and engineering is all about. This required orbital plane change to access high latitudes, like at Apollo 17 and Apollo 15. We were able to work with the engineers to increase the number of EVAs to 3, provide mobility to reach distant targets, the rover, send a geologist as a member of the surface crew. You just saw how critically important that was. And then we were even going to send roving vehicles. I want to come back to this at the end, which is indeed to try to think about how we optimize human and robotic interactions with combined rover, robotic rover, human-rated rovers for, in fact, Artemis follow-on missions. Next, please. So what was the legacy of Apollo and the lessons for Artemis? We have these 6 beautiful missions here landing on the surface. We learned huge amounts for the moon. I'd love to bore you to death with all the lessons we learned from the science, of course, but that's the foundation of our exploration of other planets, etc. Next. So what do we learn? Okay, let's take a look at some general lessons from Apollo. Okay, like Apollo, the Artemis program will be evolutionary, okay? Early Artemis missions, we're starting almost over again, okay? We need to relearn how to explore the moon. We have a new launch vehicle, new transportation system, gateway, new landing systems, new international partnership to coordinate and manage, detail roles, TBD. Okay, we got a lot of learning to do there. New astronauts, new suits, new and very extreme illumination conditions, and uncertain levels of surface mobility and EVA duration and sample return mass. These are all huge unknowns. So we can't be starting with a scientific expedition to the moon on the first go. We got to learn how to do all this, and we got to work shoulder to shoulder with engineers to optimize the scientific return. I also want to point out a number 2 here, the misnomer of mission control. It's really mission coordination. I think the best way to think about the activities on the moon and going forward is to think the American football analogy. The team, the astronauts, are on the field. The quarterback, the commander, calls the local plays, but he or she has sideline and deeper backup input. Okay, think about that. You have the coach along the sideline, you have the defensive, offensive coaches, and you got all the people up in the booths, also doing these analyses. And each one has a different perspective and provide input if the quarterback needs it. And the quarterback, of course, looks over to the sidelines for signals from time to time. And if things really get tough, okay, a timeout is called and a little bit of replanning is going on. So I think this is the best way to think about it, okay? The team on the field with a quarterback and a team. And indeed, it's not, you don't run in every 5 minutes to tell them what to do. You basically let them do it themselves and provide help as needed. So how do we prepare the team on and in the field on the moon? Well, I'd like to think about, I think it's really important to understand the concept of situational awareness, okay? So what is that all about? Basically, situational awareness can map out into the fact that when you're there, you are the one who knows what's going on in the best possible way. Yes, you can have input from the outside, but always remember, it is the crew on the surface that knows what's going on infinitely more than anything you can get from remote observations or even TV, updates, high definition TV, et cetera, they will still know better what's going on. So really respect that situational awareness. And again, the best strategy, one we included in Apollo really, was T cubed. Train them, trust them, and then turn them loose. They will be the ones who have the situational awareness, be there to help. That's why they call it a science support room, but it is not mission control, okay? Also remember Krikolev's law. I'll tell you what that is in a second. Sergei Krikalev is one of the most amazing astronauts going. He is a Soviet/Russian cosmonaut. Amazing guy. And remember that we are training for Mars. We need to practice crew autonomy. And what is Krikolev's law? This relates in part to what we've been talking about in terms of our discussion about lessons from ISS. Read this paper, Crew on the ISS, Creativity or Determinism. And what Sergei points out is that the crews are, in fact, really on ISS, minimizing the creativity and optimizing from the ground the determinism. That needs to be really fought when people are on the moon. We will be exploring on the moon. We need to optimize the creativity. Next. So a couple of other points here. What principles and guidelines to use? Well, the Artemis program goals are clear. We just heard those from Renee. They're excellent. These are the same kinds of things we had in Apollo. And not only will these be guidelines, but each one will be different and clear. Remember that all individual Apollo missions were built on a foundation of this whole list of things, okay? Geological training, classroom stuff, all of these things were repeated again and again and again with each crew. And these became more and more intensive in detail with each mission. The integration of flight operations, including flight directors and NASA management, into aspects of the training and field training. One of the best things that Gordy ever did was to get all these people out into the field to see how the sausage is made when you're doing geological investigations. Do that. That's what helped with the science and engineering synergism, where we integrated the scientific goals and objectives at all levels. The astronauts to Apollo mission director, they were on our side. They were trying to help us do all these kinds of things. And mission simulations in the field and mission control, in the field and mission control, simulate, practice. We had debriefings, lessons learned from each succeeding mission, and then put those into the next plan. Next, please. So science operations. These were structured around specific experiments, and basically there were instrument experiments of the individual LSEP, the heat flow, et cetera, but the point here is these need to be integrated into traverse planning, okay? It is really important that we develop something like the Apollo Lunar Field Geology Experiment. These are Gene Shoemaker, Gordon Swan, Bill Mulberger were the PIs. This was the key to the science support room, back room. It was an experiment, okay? We need to have people who are in charge. We need to have a hierarchy. We need to have something like the Apollo Lunar Field Geology Experiment so that it isn't just a bunch of random inputs. And also there were mission rules that set scientific and experiment priorities and serve to help and plan contingencies. I'll come back to that in a second. Next. Geological traverse planning. These were really important. They followed Apollo program mission goals and objectives designed by a small group, JSC, USGS, NASA headquarters, et cetera, implemented, interacted, and iterated with the astronauts, operations, and science community. And they always had primary and backup contingency traverses. For example, what happens if the LRV doesn't work? Well, you've got to walk. They were not scripts. That's another thing I want to just kill wherever I can. They were plans and almost never stayed the same during the mission. No one in their right mind would go into the field, Antarctica, the bottom of the ocean, anywhere, without a plan, okay? So the players in this were diverse. I won't go into them here, but there was a whole bunch of different people that had input, had reviewed these things. And it's important to continue this kind of interaction because this is how you educate people, get them on your side, and help actually put input into the final traverses. Next, please. So how to support the team on and in the field, on the moon? How did it all work during a mission? The science support back room, the Apollo Field Geology Experiment and Mission Control. Field geology team, as I think Jack described all this really well. And the back room communicated with Mission Control and the Capcom. These were done through one person. It was Jim Lovell, the Apollo 13 commander, during Apollo 15 mission, for example, because you don't want to have multiple inputs into somebody who's communicating or making the final decision. You need to have a summary of that, and you need to have somebody like an astronaut who knows what's going on. That was very effective. Mission astronaut backup crews were often observers in the back room, and there was a hotline to Building 31, the science area, science support team. So that's another point I want to make. We don't have to have everybody in the same room. Actually, it's bad to do that. You need to have a smaller number of people with inputs that can be summarized into a pyramid-like input. And the science instrument deployment monitoring, the ALSEP, don't put them in the same room. There's a separate MCC back room, have communications, but don't put too many people in that room. So let me turn to Apollo 15 now as a quick example of the first lunar scientific expedition. Next. Next, please. So let's take a look at Apollo 15 here, okay? Next slide. You're going to have to keep your finger on the slide button here, okay? So 6 months after Apollo 14, Apollo 15 was launched to the Embrian Basin rim, the Hadley Sinuous Rill here. Next, please. And you can see here that there were multiple objectives. We had basically 5 major geological objectives, which are part of the overall context: the impact basin, Maury Plains, Hadley Rill, North Complex, and secondary crater cluster. Lots of sub-objectives, which turned into, of course, goals and objectives for specific aspects of traverse planning. So lots of different scientific questions resulted in the selection of the landing site here and also in the traverse planning. Next, please. So one thing that this required was, of course, major changes. It required to change the plane of the orbiting spacecraft, the command and service module, so that the lunar module could, in fact, land at high latitudes. This was a major deal, a major change. This was done for the science, so we could get to these kinds of sites. Next, please. The second thing was that to get into here, Jim Irwin and Dave Scott had to fly over Mount Hadley, which is 14,000 feet high, and land on this side, the eastern side of Hadley Rill, which is 900 meters deep. This required a steeper limb descent path than normal. And Dave Scott said, gee, Dave, can you do this? He went in and simulated it. We can do that, no problem. That required astronaut interaction, some major decisions on the part of management and the crew. Next, please. So when they got to the surface, they did it successfully. There's the mountain in the background. That's Mount Hadley. And you can see, in fact, they landed actually on a tilt, which caused some problems getting the rover out. Next, please. The rover was beautiful. It finally worked carefully. Next, please. And the traverses, you can see here in this perspective view in the upper right, there were 3 traverses that extended to the North Complex. The first one to the Mount Hadley Delta, the second one to Hadley Delta, and the third one to the North Complex and the Rill. So that was the nominal ones, but there were lots of problems that arose, and these are good examples. There was a limb undocking issue. We were landing in 20-meter resolution images. You can see the image on the left here. There was an oxygen leak, there was a water leak in the lunar module. The heat flow drill got stuck in the ground. LRV checkout, when he first started it up, there was a voltage issue. There was a front steering, didn't work, etc. Things ultimately worked out, but in the next slide, you can see that we did not, in fact, we did not, in fact, accomplish those major traverses. The point here is that there's a lot of problems associated with each of these missions, no matter what's going on. Jack pointed out a few of these, etc. So you can see here that these traverses are not the same as this. We had to replan EVA2. There were no boulders down here. The radar data, 20-meter resolution radar data, had said, oh, it's really going to be rough and bouldery down here. Dave Scott and the stand-up EVA, and also actually on the way down, there weren't any boulders. So we had to completely replan that, focus on in-depth Hadley Delta site here, okay, and indeed descoped EVA3. It took a significant amount of time to extract a heat flow core, but that was the highest priority experiment. We had to abandon the North Complex objective here, and we had to shorten all the traverses. So next, please. Nonetheless, it was a huge success. Okay, here are the geological maps in the middle there. You can see as Dave Scott is anxiously waiting for Jim Irwin to take the picture and get on the rover. Next. So they did a superb job. They did a beautiful job. 1 SEVA, 3 EVAs, 7-kilometer radius, the limb, 30-kilometer totals, and 77 kilograms of rocks and soils. Beautiful, beautiful exploration. Next, please. And you can see here, they found the Genesis rock, which is one of the major things. Dave Scott spotted plagioclase twinning from about 5 meters away. Okay, the green pyroclastic glass beads. You should go back and listen to the transcripts. Listen to the voice recordings as Dave discovers this. 40 years later, Alberto Sol discovered water in these glass beads, revolutionized our thinking about the moon. Next, please. And of course, we did a lot of examination of Hadley Rill, not just the rocks at the edge of the rill, but also the outcrops on the far side of the rill, etc. And on the way back on EVA 2, I believe it was, Dave Scott spotted this rock, and they were saying, Dave, get back to the rover, get back to the lunar module. You're running out of oxygen. You're behind the timeline, etc. Dave said, listen, I have a problem with my seatbelt, because he spotted this vesicular basalt, which we had talked about before as being really important for understanding gases and volatiles in the magmas. And he stopped, did an unauthorized stop. He likes to call it captain's prerogative, commander's prerogative. Got it, returned it, and that's known as a seatbelt basalt, and it's told us a huge amount. Next, please. So the bottom line is, let's go on to look at Apollo 16. Apollo 15 was a great scientific expedition. Apollo 16 was different, okay? So next, please. John Young and Charlie Duke went down to the surface. It was launched 9 months after 15 to pre-Mare volcanic activity into the highlands to look at what we thought were volcanic activity associated before the Mare, but after the main part of the highlands. Next, please. Now, when we look at this, after John and Charlie got down to the surface, they immediately recognized that we're not in Kansas anymore here, folks. These are not highland volcanics, but basin and crater impact ejecta. So
Jim, if we could wrap it up when you're ready, that'd be great.
Next, please. So they did a beautiful job here. The point here in the next slide, I will tell you, is that this is very much like, next, please. This is indeed very much like the South Circumpolar region that Artemis 3 Plus will discover, okay? We'll explore. The bottom line here is that you are not dealing with a bunch of different specific objectives like Mare, highlands, rills, etc. But in fact, it's going to be really different. It's outside the Apollo zone, but it's going to be like Apollo 16, where you don't actually know necessarily the provenance of individual samples. That's something we really need to keep in mind. Next. So I want to point out that this is a good example on Apollo 16 of astronomy from the moon, the far ultraviolet camera spectrograph that George Carruthers designed and built and was flown on Apollo 16. Next, please. And so let's go now to some specific lessons learned, and then we'll wrap it up here. To wrap it up.
Yeah, if we could wrap it up, we got a lot of questions.
This is it. Okay, so let's study the Apollo EVA and surface operations. Study the foundation pyramid involved. Okay, basically, we have here a necessary. It is really critically important for science and engineering synergism. Work shoulder to shoulder with the engineers and the managers, etc. From day one. Day one. Start now. You should have started weeks ago, etc. We all should. Listen to the Apollo 15 voice transcripts and recordings. This is the best thing you can do to get prepared. Listen to the excitement, listen to what they learn, listen to the inquisitiveness. All of these missions are evolutionary. The first Artemis missions will not be Apollo 15 to 17. Learn and plan accordingly. South Polar Exploration Planning. You're in the highlands. Think Apollo 16. Incorporate robotic rovers for interpolation and extrapolation. Situational awareness. Encourage, train them, trust them, turn them loose. Avoid meddling with the crews on the surface, but help them out. That's a science support room. Remember Krikolev's law, respect and encourage creativity. Fight determinism, which is like, here's your rules, here's your timeline, go do it. Murphy's law, if something can go wrong, it will. It will, it does, it always does. That's why we have contingency planning. And we're heading to Mars, no real-time support. It's really important that, in fact, we learn debriefing, briefing, optimize science support, the two-way sequential briefing, debriefing. When the astronauts get back from their EVA, have them debrief you, then you debrief them in a later time, then you have them tell you what they think, have them tell you what they think about the plan, and then you pass up a final plan. This is critically important because that's the way it's going to work on Mars. And again, a science support room, it should be a mission control, but separate location for the deployed instruments, science support room, and it needs to have real-time focus. Science Operations Center should not be in the Mission Control Center, but in fact should be somewhere else that can easily communicate, okay, but just not all in one room. So the
Okay,
last
Jim,
slide,
I think
that's it.
we're going to have to wrap it up here.
That's it. And if you just go to the last slide, I'll point out that, in fact, you can go to the next slide. The next slide. Okay, that's it. So I just point out that in this presentation, in the last slides, which I was not going to cover, are guidelines to answer all the questions that you guys were asking, okay, for this breakout groups. Thanks a lot. Sorry for the, I mean, hey, there were 6 missions, okay?